So welcome back, everyone. Let's get started. So thanks for showing up on the day the homework's due. We struggle with attendance on those days. I'm not sure if it's better to put the homework due right before the lecture, like I do in this class, or at the end of the day of the lecture, or like the night before. I'm not sure what I can do to get kind of people to still come to class after they've been, I don't know, not staying up all night working on it, but do you guys prefer having the homework due like it's like at midnight on a certain day? I saw yeses and nos. Okay. Or is it better to be due kind of during the middle of the day? Is that kind of, I can make it due earlier, but like, right. So, all right. So I saw I was getting mixed reactions on this. Okay. Well, if there's strong opinions and kind of thoughts behind those, I'd be interested to hear, but I always get mixed reaction. I think a lot of classes have to do like on midnight. Is that pretty standard? And then you stay up to midnight and you're like, okay, I can go to sleep now, and that's good. Or yeah, but if it's due in the afternoon, you're like, maybe I'll do it in the morning, and then maybe it doesn't get done. Or you can stay up as late as you want to finish it. All right. Hopefully this was probably kind of the most time you'll spend programming in an assignment. Hopefully it wasn't too bad. So that was due today. And then if you haven't finished it yet, you can turn in. The late penalty isn't too high to turn it in the next couple of days. So let's get into the lecture. So we're going to talk about the singular value decomposition today. Who's seen the singular value decomposition in your linear algebra course? Okay, so most, maybe about half of you. Who did not see it in their linear algebra course? All right. So that's why we need to cover it here, because it's not always covered. If I was teaching a linear algebra course, this would be kind of the star of the whole course. Okay, this is, I think, the most important thing to come out of linear algebra, other than things like addition and multiplication by like vectors and matrices, right? So this is the single kind of most important operation for dealing with data using linear algebra. So we'll basically be spending today's lecture on this, giving you some intuition about it, how to use it, what it means in the context of our problem. Nothing much to say about the schedule. I will get homework 5 out by Monday, so you can start working on that. But otherwise, we're just in a normal place in the schedule. All right. All right, so let's start by revisiting that we have our input. Okay, we're going to think of this as a set A. We've been thinking about this as A1, A2, ... N. So these are N data points, and they lie in our D. And it's going to be equivalent and more useful today to think about this as a N by D matrix. Okay, so we're going to use linear algebra today. And so we're going to turn our data points. Each data point is a D-dimensional vector, and we're going to stack them into a matrix A. And we're going to kind of look at what we can do with this using linear algebra to give us the answer to our question, which is, the goal is we want to find a basis or a subspace B, which was defined by this set of vectors, right? And these were such that K is probably going to be less than or equal to D. Usually less than D is what we want. We're going to have that each of these vectors, the norm is going to be equal to 1. That Vj dot Vi is going to be 0. So these are going to be orthogonal to each other. VI, VJ. So they're all going to be orthogonal to each other. And with this, we can define a projection operation, pi of B, of each of the rows A, right? We're able to define this projection, okay? And this was such that we are in some high dimensional space. I can't draw D dimensions. Let me pretend this is RD. We're going to choose a subset of vectors in the space. Let's say this is V1. This is V2. These are some unit vectors in the space. So here I've kind of drawn 3 dimensions, and this K is now equal to 2, right? So we can think maybe this is 3 dimensions, K is equal to 2. And then we're going to have a subspace here, and I want to take some data points, say A1 here, right? And I'm going to project this is pi of B of A1, okay? And so I want to be able to define this projection, but I don't just have one data point. I have these other data points. This is A2, maybe A3 is below and is projecting up. This is A4, and I'm going to have a whole set of these, and I want to project them all onto this subspace, okay? And my goal is to choose VB so that VB star is going to be the set V1 up to VK, which is going to be the arg min over the set of VB, which is minimizing the sum of all of the data points 1 through n, where I'm looking at the distance from AI projected onto this space squared, right? So I'm looking at all of these residuals, right? So this is now the residual, and I want to minimize the sum of the squared residuals. So I want to find the K vectors so that the projection onto the subspace they define minimizes the sum of the squared residuals. That's what my goal was. Most of Monday's lecture was defining just how the projection actually works, right? And we got to this point where we said, this is our goal. We want to minimize the sum of the squared errors because I told you, I kind of tried to allude to reasons why we chose the sum of the squared errors. And one of those was going to be that there's going to be a nice computational way to compute this VB star, okay, this optimal set. We're going to be able to compute that. And so we're going to do this with 2 ways today. One way, or we're going to do with one way today, we're going to use linear algebra operation, the SVD, to give us the answer. Okay, we're going to run the SVD, which is a command you run inside of any kind of reasonable or programming language or processing data, and you'll be able to read off of the SVD the optimal answer for this. And then we'll see how to compute that next week, Monday. We'll see one way how to compute what we need from the SVD. Okay, before I move off this slide, one more thing I want to say is that there are kind of 2 outputs here. We either have pi of B of AI, and this is going to be a vector in RD. Okay, so in order to compute the residual, I need to do a vector subtract. Between these 2 vectors, they both need to live in RD. In order to compute this, I have to subtract 2 vectors. So I'm projecting to another p-dimensional vector that happens to live on the subspace. And with this, I can compute things like like the residuals. So this is kind of one output. The other output is that I've got this vector AI v1 dot AI v2 dot 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 AI vk, and this lives in Rk. So by getting the coordinates, so I can write this now in this d-dimensional space as a vector a1 v1 comma a2 v2. Right, so this is now a two-dimensional vector where this length is a1 v1, and this length is going to be a1 v2. I get these two coordinates. I've got a new coordinate space here to represent this point. And so these are two possible outputs I can get out of this. Either a point in a vector in RD, or a low-dimensional representation. Now it only has k coordinates, maybe only 2 coordinates here. And that's how I get the dimensionality reduction. Okay, and we're going to get both of these outputs out of the SVD today. Depending on how you reuse the elements of SVD, you get one of these two representations, and we'll see them in kind of in different ways using the linear algebra. Okay, so okay, great. So what is the SVD? Okay, the singular value decomposition, often just called the SVD. Okay, and it is going to be a way to take my matrix A, and I'm going to rewrite it as the product of 3 matrices, U, S, and V transpose. Okay, and so I think I'm going to try and illustrate this through like a picture with like rectangles and stuff, and hopefully kind of make sense of what this is all about. So our input is A, right? We're going to remember that we said that this was D, and we're going to be thinking about when you have more observations, more data points, then you have dimensions. Well, think about that. You can do with D is larger than N, everything will work the same way, but this will kind of be usually the right thing to keep in mind in this case. And we want to reduce the number of dimensions, even though the number of data points is bigger. Okay. Okay, and so this will be, if I rewrite this, it's going to be a product of 3 matrices, which are going to be, in general, larger than A. So this seems like not very useful, but these are kind of capture important information. This one is U. U is going to be, U is N by N. So it's an N by N dimensional matrix. We're going to have the matrix S. All right, so this is going to be the matrix S. It's going to be an N by D. Remember, A was N by D, so the same dimension as A. Sometimes you actually don't write this as an N by D matrix, but if you don't, then you can't kind of recompose them together. Okay, and then we're going to have another matrix V transpose. Okay, V transpose is going to be D by D, and I write it as the transpose. Why don't I write U as a V and then not store it as a transpose? We'll try and get some insight into it. Okay, and so it's going to be the product of these three matrices. So I take this as the input, and it outputs these 3 other matrices. Okay, they're bigger. They can't possibly contain more information, but they're better structured than A. Okay. Okay, and to look at this one captures, the S matrix captures things called the singular values is going to be an S. And S is the easiest to kind of understand, at least at a at a high level here, in that all of the information is going to lie on this diagonal. Okay, so this element here would be called SJJ, right? The jth column and the jth coordinate. Okay, and what I know is that everything below here in this space, everything down here is going to be a 0. Okay, and in fact, I also have that everything off the diagonal, these points are also going to be all 0. Okay, so all the information is contained on this diagonal. Okay, these terms here, SJJ is often called sigma J, and this would be called the jth singular value. Okay, and this will tell us, this will be if each one of these is a scalar value, right? It's just one entry in the matrix, so it's just one number, and this will tell us how big something is. Okay, we'll explain what is so big, how big something is, what that is describing later, but just kind of mechanically, that's what this matrix is. Okay, this one's easy to understand. Okay, let's next look at, next look at the U matrix. And for the U matrix, there's kind of a very important kind of demarcation between the first D columns and the n minus D columns over here. When I multiply this matrix S by U, this part is all zeros. Okay, so when I multiply it by U, that means you kind of turn it on the side and you kind of slide this part down here. That means that whatever is in this part of the matrix gets multiplied by zeros. So it does not really matter. Okay, so this part kind of is going to get canceled out by the zeros in the S matrix. So this part over here does not really matter. Okay, so we only need to look at those first D columns of U. Okay, so let's look at one of these columns. Okay, this column here, we'll call this UJ, and this will be called the this will be called the jth left singular vector. Okay, so now the columns which are left are kind of the interesting vectors, and this is a d-dimensional vector. Okay, and it is called the jth left singular vector. I'm going to have the property that each uj is going to be equal to 1, and that uj dot uj prime is going to be equal to 0. So these are all going to be orthogonal to each other. Okay, that's also going to be true for the columns over in this region, but those don't matter so much. Okay, so we can mostly just ignore them. I also know that U is going to be an orthogonal matrix. Okay, so the whole matrix U, the whole uppercase U, is going to be orthogonal. Okay, and well, that's true if all the columns are of norm 1 and they're all going to be orthogonal to each other. That makes this it's going to make it an orthogonal matrix. That kind of means it kind of limits what it can do. It can't control any kind of scale information. It can only kind of change the basis of it, and we'll kind of try and see what that means in a bit. We're mostly not going to worry about U though. Okay, so now that I've told you this, we're mostly, when you think about a tall, skinny matrix A, usually U is not as important. What's more important is the S matrix and the V transpose matrix. Okay? So now the V transpose matrix, it does not have this effect that some of its elements are multiplied by zeros in S, as long as A is both tall and skinny. And we're going to look at the rows of V transpose. Okay? If it was V, we would look at the columns. Okay? If it was V, we'd look at the columns, but it's transposed, so we're going to be looking at the rows here. Okay? And so this would be called Vj, and this is going to be the jth right singular vector. Okay? And so we're also going to have the property that each of Vj is going to have a norm 1, and Vj dot Vj prime is going to be equal to 0. That means that the matrix V is also going to be orthogonal. Okay? So that means, again, it's not going to have any scale information. It's just telling us kind of, again, because these vectors define a basis, I can do things like project onto them. Okay? And that's not going to tell me the scale of something. All the scale information will be pushed into the singular value matrix S, and that will tell me how much information is associated with these. Okay? So in fact, what's going to happen is that this vector here, Vj, will be associated with the jth singular value. So there's an association between the singular vectors and the singular values, because S is kind of a diagonal matrix, and V is going to be orthogonal. Only the jth row of V will interact with the jth singular value. Okay, in fact, I will be able to write I can write this as a sum of j equals 1 up to d of, let's see if I do this with colors, uj sigma j Vj transpose. Okay, so I can write it as the sum over these terms, where I just take the j column here, I multiply it, scale it by the scalar value, and then multiply it by the vector over here. How can I multiply an n-dimensional vector with a d-dimensional vector? How does this make sense? So if I made a mistake, am I allowed to do that multiplication? What do you think? Did I make a mistake? And this is one of those tests to see if you're paying attention, or this is right up here. Okay, so who thinks I made a mistake? And who thinks it's okay? Okay, good. Okay, I'm pretty sure I didn't make a mistake here. Okay, so why is this valid then, right? Is this a legal operation? What's the dimension of uj? It's n by 1, right? Okay, so I can multiply n by 1 times a 1 by 1 times a 1 by d, right? Always the dimension next to each other has to be valid, and I can okay, so it's n by 1. If I ignore the scalar part, it's n by 1 times 1 by d. Okay, this is a valid operation. So what is the dimension of this internal part? Once I multiply this term for just the jth term, what's the dimension of the output of that? Yeah, this is going to be in n by d. So this is going to give me a rank 1 matrix the same size as this for each column scalar row combination is going to give me a rank 1 n by d matrix. And then I'm going to add d of these together. Okay, so because S has only information on the diagonal, the rest of the kind of the other parts don't interact with each other. Okay, and so this is a very special structure that allows me to do this, right? It has to be very special that I'm able to decompose A into these nice pieces. Okay, and so they're structured such that there's the property. So sigma 1 is greater or equal to sigma 2 is greater or equal to sigma d, which is greater or equal to 0. Okay, so the singular values is important. And they tell me how big something is. So that means the first one is somehow the most important. Okay, and then the second one is the next most important. And they each give me a rank 1 representation of the whole matrix, and I'm adding these together. I'm doing these components of the matrix that each tell me something about it, and they're in sorted order for me. Okay, so again, this will be, for today's lecture, this is just a single function we're going to call in any programming language. We'll do it later in Python this lecture, and it will just give me all this information in sorted order. Okay, yeah.
I just wondered, will we tell us everything about, I mean, all the values that way in the real world, we just kind of live these things.
Yeah, we'll get into this. This will kind of develop. Today's lecture will be mostly linear algebraic and kind of the geometry, and we'll look at some examples of where you would use this. But you have to, it only makes sense to apply it on those examples I talked about on Monday, like a bunch of weather stations or a bunch of kind of these consecutive strips of stock prices or these word vector embeddings. Those settings, it makes sense to do this, and we're going to try and capture a low dimensional representation of this that captures most of the information in those. We want to find a smaller dimensional representation that has as much of the information in it as possible. And so that's kind of towards the fourth lecture in this series, we'll give a little bit more kind of a more directed application. We'll use this inside of something else that we'll see why this can be useful to want to do. All right, great. Okay, so I want to give more intuition about kind of what this is actually doing, because even if you have seen this before, it probably still how to apply it is still not super clear. I want to focus first on the right singular vectors. These are nice because they're d-dimensional, and we thought of our data points as the rows. Remember, we have our data points here were these rows, AI, and these were also d-dimensional, right? So it's hard to get an n-dimensional vector from the left singular vectors to interact with the d-dimensional vector, but these are d-dimensional, so these can interact nicely, and they're orthogonal, so they actually fit the bill of what we want to do for the projection. So let me try and draw another picture of how to think about what's going on here by just drawing the first two. So I want to think now that I have some data, and we'll think that for now that the data is centered around the origin. Okay, but it's living in, say, a three-dimensional space, and each of these are supposed to be dots, but they're small lines. Each of these is like one of the data points, right? So this is A1, this is A2, this is A3. Okay, and so what we're going to hope is to find a low dimensional projection to place all these points on. And what I'm going to claim to you is that what we're going to choose are these directions. V1 in a data set that looks like this, V1 will look kind of like this. Where it's kind of, if I see kind of a lot of variation in the data points this way, V1 will kind of be aligned with that. And that there's going to be a second axis that's orthogonal to it. This will be V2. So somehow V2 will represent this. And then what's going to be even neater is there going to be some sort of elliptical structure that looks like this. Okay, so I kind of want to draw and just these two axes, I want to define an ellipse. And I do this by thinking of like take these directions and how far out do they go? This how far out they go is going to be associated with sigma 1 and sigma 2. These are the angular values. If I have two orthogonal axes and a scale associated with them, that's going to define this blue this blue elliptical structure. The same way I can define a so well, I could draw a three-dimensional ellipse as well, but I would need a third axis for this. So right now I'm trying to draw a two-dimensional ellipse that lies in the subspace, the span of V1 and V2 and the origin. So that's right. So if sigma 1 and sigma 2 were the same, I would stretch them in these dimensions the same amount, and it would be a disk, a circle. But because sigma 1 is bigger than sigma 2, I've stretched it more in this direction than I have. Okay, and so the sigma 1, sigma 2 tell me how much to stretch in each of these directions, and the V1 and V2 tell me how to orient, what directions I'm allowed to stretch on. Okay, and so the right singular vectors and singular values define an ellipse, and for any size k between 1 and d, it defines a k-dimensional ellipse. So if I can imagine this lying in three-dimensional space, this is a two-dimensional ellipse that's going through here. It's centered at the origin. Okay, and so this is in particular, this will define in various ways, we will quantify the best fitting ellipse to the data. Okay, it's going to find the ellipse that somehow is defined by the data. So if I looked at the average, if I kind of take some direction here, if I looked at some direction, some direction x, okay, let's say this is a unit vector, right? So I looked at some direction x here, and I said, on average, how far are the data points from the origin in this direction x, or how spread out they are from the origin? What does that mean? That means if I look at the expected value of x dot ai squared, and then I think I took the square root of this, right? So how far in this direction x do I expect the data point to go? That's going to place me on this ellipse. It's kind of the average variance of the data points with respect to the origin in that direction x, and it'll define that for all directions x. Okay, so this is what the right singular vectors and values will give me. Okay, this is kind of a geometric way of thinking about what's going on here. All right, look, let me try and give you a more grounded illustration in numbers. What's going on here? A different way of showing this. Let's look at a concrete data set now. Yeah, let's say now my data set A is going to be defined as 4, 3, 2, 2, -1, -3, -5, -2. Okay, so this is a data set in 4 by 2. So it's n is equal to 4, and I'm in 2 dimensions. And I've chosen this in a careful way so that I can draw all of the data. So point A is like 4, 3. So A1, this is the first point here. 4, 3 is right here. I can draw 2, 2 is going to be, this is A2. A3 is going to be -1, -3. So this is A3. And A4 is -5, -2 is about here. Okay, so I've kind of drawn an actual data set here. So it's a small enough one that I'm going to be able to draw it and get some intuition to myself. All right. I chose this very carefully, so it's in 2D, so I could draw it, first of all. And second, so it's centered at the origin. If it's not centered at the origin, if it's not averaged at the origin, this is going to be kind of wonky to think about what's happening. And again, I mentioned we're going to fix this assumption things are centered at the origin later by forcing them to be centered at the origin. It'll be pretty simple. Okay, so I want to now, if I were to compute the SVD of this, right, I'm going to get out some quantities. So if I do the SVD of A, I'm going to get that V is going to be -0.8142 -0.5805 -0.5805, okay, and 0.8142. Okay, so this is again hard to imagine just looking at the numbers, but this is a 2 by 2 matrix. Okay, it's supposed to be D by D. So this is okay. And let me also write out S. S is going to give me values of 8.1655, 0, 0, 2, 3, 0, 7, 4, and then 0, 0, 0, 0. Okay, so this is the right dimension for V and S. I'll tell you something about U later, but for now it's, again, we're going to try and understand this picture. We don't need U in this picture. Okay, so what's going on here? So let's try and understand what's happening here, but I'd like to, so the first way to think about this is because we're in 2 dimensions, I can start by drawing a picture with this is the original coordinate axis, and I know that V1 and V2 must be, again, I haven't done V transpose. So this is V, so I'm looking at the column vectors, right? So this guy is V1 and this is V2. This is V1 and this is V2. Okay, so they're unit vectors up to 4 digits of precision. So what's -8.14 and -0.58? Where is that? That's going to be about here. This is maybe, let's say this is V1, right? So it's going to be a unit vector. It lives on this ball and then on the circle. And then V2 is going to be orthogonal to it. down here. Oh. Okay, so this is going to be V2, right? That looks about right. Okay, that makes sense. These are orthogonal vectors. Okay, so how do we think about what's going on here? Well, I want to kind of think about this through what happens when I do, remember, I have A, and I want to say what happens if I do A times a vector X, okay? X will be a vector in a two-dimensional vector, and this will be equivalent to SV transpose X, right? Because this term is equal to A. Okay, and so what I want to compute now is what is V transpose X and what is SV transpose X to kind of show you what is happening. Okay, what these different components of A are doing to this vector X. And so I have an example prepared where X is going to be equal to 0.243, 0.970. Okay, so this is approximately a unit vector. So I'm going to have X is going to be about, this is about the vector X. Okay, so what happens when I multiply this through here? And so I can now draw this also here. This is X. Okay, so what happens when I multiply X times V transpose? What is happening here? Okay, so what's happening with V is it's going to change my basis. I'm going to get a new coordinate frame doing this projection. It's going to go back to this picture where we had some data point, and then we're drawing in the coordinate frame of V1 and V2, and we're getting a vector like this. So it's giving me a new way to define my coordinates, and that's what's going to happen with this first step here. Okay, so this one is going to give me a new coordinate frame. Okay, and so what I'll be able to do is I'll be able to redraw my basis based on V1 and V2. And I know that this is a unit ball again, if I can draw it properly. Okay, so again, there's a unit ball, but now I have the basis defined by V1 and V2. And what happens to X? What's going to happen to X when I multiply it here? Okay, so well, the first coordinate is going to be X dotted with V1. What's X dotted with V1 going to look like? It's the projection onto here. Right, so I'm going to do something like a projection onto here. Did I draw? I mixed these up. I didn't draw V1 and V2 correctly. Now that I'm seeing this. Why is this the wrong spot for V1? Yeah, it should be negative. It should be negative. Yeah, it should be down here. So let me fix them. Does that make sense? See how I? Yeah, I need to swap them. So let me redraw them here. Okay. So I'm going to have V1 is here and V2 is here. Okay. This looks right. Okay, so now I've messed up my projection. Okay, so now I need to fix how. Okay, now this is a little trickier. How do I project onto V1? Okay.
Because it's projection, where V1 would be in its own negative space, so you just project it down to, say, V1 backwards, you project it down.
Yeah, right. So V1 actually defines a line that goes for the origin, and my projection onto V1 is actually to here. This is pi of V1 of X is this point from here, and this value is negative. Okay, so now what that means is that x's first coordinate is going to be negative. This is going to be, this is the first coordinate. This value is going to be x dot v1, and it's going to be negative. Okay, and then the other coordinate projected onto v2 is here. This is pi of v2 of x, and this one is now positive, right? So now the v2, this value will be x projected on dot with v2, and so that means that my x in this coordinate frame is now up here. Okay, so this is now a representation of x, but I've changed the coordinate frame. Okay, so it's the same point x, but now I'm writing in the coordinate frame of v1 and v2. And so if I calculate this, v transpose x, what value am I going to get here? Let's guess what this value is. I don't have this written down, but we'll calculate it in Colab in a couple minutes. I'm going to guess it's going to be about negative 0.5, positive 0.9. Okay, it's going to be roughly negative 0.5, positive 0.9. Roughly in there. So I've changed the coordinate frame of x. And so for every data point, what v is doing is it's giving me a new coordinate frame of the data. Okay. And so now I don't have room on this slide, but I want to make a copy of this. Okay, let's do a new slide and see what happens now where I have some, and I'm gonna now call this point. So it's gonna technically be a different point. So let's call this actually a point P. P equals V transpose X. Okay, and it's in this coordinate frame defined by V1 and V2. And now we're gonna see what happens, right? So this P is V transpose X is equal to V1 dot X, comma, V2 dot X. Okay, and now I want to see what happens if I do Q is equal to S V transpose X, which is going to be S times P. Okay, and if we remember, our matrix S was something like, was 8.16, 0, 0, 2.3, 0, 0, 0, 0. Okay. So what happens when I now multiply this by S? And so now I want to draw this as a picture again. Let me draw a small version of this. This will be the origin. This will be V2. This will be V1. Okay. And so there used to be a small circle down here. And so P lived on the circle, but now I'm going to expand this. I'm going to stretch it. I'm stretching the first axis by 8, right? So I'm going to now and stretch this out. The first axis is going to go out. This is about 8. I didn't count exactly, but it should be out about 16 spots. Okay, and the second one by 2.3, so to about here. Okay, and then it's going to define, instead of a circle, there's going to be an ellipse like this. Okay, something like this. And now P is going to get stretched out to Q. All right, so this makes sense. I was on the smaller circle, and now I know how to stretch it. It's going to be an axis aligned ellipse because I'm just multiplying by these this diagonal matrix. So I know how to stretch it. I know which axis to stretch on, and I stretch the x-axis a lot and the y-axis by a smaller. This tells me how much is stretching. Okay. So does this make sense? What's wrong about this? What should the dimension of Q be? Once I've multiplied, Q is S times P, or P was a two-dimensional vector. S is a 4 by 2-dimensional matrix. Right, so what is the dimension of Q? What should the dimension? I've drawn it as a two-dimensional point. Is it two-dimensional? No, it's four-dimensional. So what happened to the other dimensions here? I haven't drawn them in the picture. So where are the other dimensions? Yeah.
Essentially, we multiply them by 0, so they don't need 0.
Yeah. There are two other dimensions coming out of the screen. You visualize two of them, but imagine there are two dimensions coming out of the screen here. But every data point originally in the original two-dimensional space is 0 in this out of the screen. So everything has to live on the plane anyways. Okay, so it can't. So I've represented it as four-dimensional, but those parts, they come a distance of 0 out of the plane. So I'm kind of so I've not drawn them. Okay. So, but there are two other dimensions now. Okay, so let me point out this is in R4 and Q equals, Q1, Q2, 0, 0. Right. So these third and fourth coordinates are going to be 0. And that'll be true of any two-dimensional point I start with. Okay, so that's kind of what the S matrix is doing. What's the U matrix doing? It's kind of assigning a weight onto each of the data points. It gives me an n-dimensional vector in a coordinate frame where it says, okay, Q has a certain length now. How much of that length is associated with each of the rows of the matrix? Okay, this is a little bit hard to think about. We won't need to think about this here. Okay, so I won't say too much more about it. Okay, let me go and let's jump to Colab a little bit. And this is linked off of, where is it? Linked off of here, this Colab link. And okay, so what did I do? We're going to use a new, I don't know, we're going to use SciPy, which is a library that does kind of scientific computing computation inside of, it's kind of an extension of NumPy, but it's going to have this linear algebra package inside of it that's going to have all this magical stuff that's going to give us the SVD by calling a command inside the library. I'm going to load in my matrix. It's the same one I told you about, hopefully. Okay, and you can see I've loaded in the matrix A. I printed it, and then call this from the linear algebra package SVD. Hey, and it's going to output USD transpose. Okay. I haven't printed them out yet. Okay, let's go and print these. But that's all I do. That's going to give me this data, and then I can just use the data. Okay, if I print this out, U is going to be a 4x4 matrix full of each of the columns will be a unit vector. They'll be orthogonal to each other, and you can check that if you want to. F, it didn't give me a matrix. It just gave me two values. Okay, so there is a command, hopefully I remembered, called below, where you can turn this into the matrix of the right size if you want. But it said, look, the only things that matter are actually those two values on the diagonal. So I'll just give you those two values. And then V transpose, it gives in Python, it gives it as V transpose. In some other languages, it might give it as V or something, but here it's given as V transpose. The only difference in the transpose, there's symmetry here, and this is not so unusual for two-dimensional cases. It switched the sign on. Okay. Yeah, so print S. If I, yeah, we can. So let's go through this kind of operation I did now, where we took this vector X, which I said was a unit vector. It's close to a unit vector now exactly. So let me normalize it. So I turn it into a unit vector. Okay, so I normalize it, I print it 0.99999, basically 1. Okay, now I multiply it by V transpose, and I got out negative 7.6, negative 6.4. How close was that to what we had? Oh, I think I did something as a negative value in the second coordinate. And so this happens to whether I use V or V transpose for my vectors.
Actually,
So I did. So what did I do different, guys? My V1, I think I wrote V instead of V transpose, and that, oh, I put this the negatives on here. So this should be, so I should have made, okay, so what happened was this negative should not have been here, and it should have been on this one. And that would have been the correct one, but this gives me a different orthogonal matrix, which gives me a slightly different answer. Okay, so that's a valid, I believe it's a valid orthogonal matrix, but it's not the singular vectors for this data. V1 should have been pointing, what I should have had is that V1 is basically here, right? It's pointing along the kind of the biggest direction of variation. It happens to be negative, but the sign of V1, I could flip it and it doesn't really change any information in the, it just changes the sign in the representation. So these are only precise up to signs. And it looks like, oh, so if I had flipped V2, it would have been, V2 could have been the negative of this, which is what that change in red would have done. Okay, good. This is interesting. If when I called this on a different day, where I got the data that I used in the lecture before, it decided to make V2 the negative of V2, which is this row here. It flipped the sign on them. And these singular vectors are only unique up to signs, and there could be other rotations if there's a tie in the singular values. The sign thing can definitely happen. It's 50-50 basically. The rotation up to a singular value of the singular values, we won't talk too much about. Okay, that will if that really matters for what you're doing, you're not doing something stupid. Okay. Okay, so that's what happened here. That's why it's a little bit different. So it's giving a negative. So I think what we probably got was negative 7.6, positive 6.4. This should be about what we got. And if you look at the norm of it, it's still 1. So it's still unit vector. I haven't changed the length information, only the representation in a different basis here. Okay. And now we multiplied by S, right? I had to turn it into a diagonal matrix. I turned it into a 2x2 diagonal instead of a 4x2 one. And then I multiply P by S, and I get this out, and I've got this stretch vector now. right? And this should look like what we had here. I guess it should have stretched it actually more over here in this way. I didn't draw that quite right. Okay, but this kind of, it's a stretching up here, and the length was now like 6.3 instead of 1. So I've stretched the length out. And this tells me how much to stretch it out depending on where it is. Okay, and if you look back where we were, this was 6.21, and the second coordinate is negative, but that's because we swapped the signs of here. Everything is symmetric up to the signs. Okay. We can now also multiply by u, and we got this nice so I concatenated some these zeros on here, and then I multiplied by the U matrix, and I'm printing, so I've concatenated the zeros, multiplied it, I get this 4-dimensional vector. Okay, that should be the same thing as if I multiplied a dot x, right? And that's what I got, the same 4-dimensional vector. So by multiplying by pieces, I get the same thing as if I multiplied them all at once, or if I multiplied by the original matrix A. Okay. Okay, we can also recover directly the original matrix A. I needed to, again, concatenate zeros onto my S matrix, but then I do U times S, fill that with zeros, times V transpose, and the output of this is our original matrix. Okay, so we got our matrix A. So everything checks out up to the sun. Great. Okay, so let me tell you, great. So I have kind of mechanically, hopefully it shows you a little bit what's going on under the hood and why this is useful. What is, if we remember, again, we have the input A in N times D in general, and then we can call the SVD of A and get this US V transpose. And in particular, V is going to be V1, V2 up to VD. Okay, and remember, my goal was going to be the arg min of B, right, the subspace, so that if I do this sum of squared errors times the projection onto the subspace, that this was minimized. I wanted to choose this VB, or really it's the basis defined by VB, so that the size of VB is equal to K, right, for some K. And so what, hopefully you've guessed what it is by now, but the answer to this is V. So I take the first K of these, and this gives me the answer to this optimization. I can just take the first K right singular vectors. They're all length 1, they're all orthogonal to each other, and they're ordered by the singular values that tell me how important they are. And so the answer to how do I define this least squares minimizing projection is just to take the top K right singular vectors. Okay, so this gives me the answer to the question we defined on Monday for dimensionality reduction. So I can read it directly off of the information from the singular value decomposition. Okay, and this is true, again, all right, given that B contains the origin. Okay, so it just kind of gives me this answer. I want to relate to, there's another thing we can say from here, is that what is this quantity and this is B star, the optimal one now. What is this quantity? I want to tell you that this is going to be equal to this kind of really neat fact, k plus 1 up to d of the squared singular values, right? So this is the bottom d minus k singular values squared. Okay, so I can actually write down exactly what the error is. The error is also calculated for me, right? My sum of squared errors turns out to be from k plus 1 up to d. The remaining singular values I didn't use. The sum of those squared singular values is exactly what my error is here. Okay, so this singular values are capturing the error or the amount of information associated with these little subspaces here. Okay, we have a few minutes. Let me just kind of go through this sort of calculation here. So I can write this down. Okay, and I can expand this. I can write A from j equals 1 up to d as Vj dot Vj AI. Okay, so I can move A is this. I've changed the basis to be Vj, the Vj basis. I've used all of it. I've gone up to D. I've gotten the full basis here. And so then I've done this term, in fact, right here is the projection onto Vj of AI, right? That's my equation for the projection onto the one-dimensional vector. Okay. And now I subtract off the projection onto the best rank K approximation, or the best K approximation. So that means here I only do j equals 1 up to K of Vj AI. Okay. So I've only, it's important on this one, I've only made it up to K. Okay, on the projection, because that B only had the first K of these, right? And this is where VB equals V1, V2 up to VK. These are the top K right singular vectors. Okay, so now what that means is, because I've written it out this way, you can see there's some stuff that cancels. Right? A bunch of the first K terms cancel. So I can write this as sum over these I terms, sum over J of Vj AI. Okay, but I can start now at K plus 1 up to D. Okay, and now I only, the first from j equals 1 up to k equals k is on this term and this term, and they cancel. What's left is when I start at k plus 1 up to d. Okay, so I've just canceled out the first k terms, which are the same before and after the minus sign. Okay, so now I can apply the Pythagorean theorem to do another cool trick. Okay, so I'm going to sum over the I terms, but now I'm going to be able to move the j equals k plus 1 over d on the outside here. And this works because Vj prime are going to be orthogonal to each other. Because that's true, I can decompose this squared length, that's the norm of a vector, in the basis of these orthogonal Vj terms, and I can pull the sum, this sum outside this norm. Okay. Now I'm going to look at this. I can take this norm and I can say this vector Vj is a unit vector. Okay, so I have now that Vj, the norm of it is equal to 1. So that means I'm going to be able to drop it from the norm. And this is just a scalar term. So I can pull this out. It's squared when I pull it. And I'm going to pull it out and square it. And the Vj will have a norm of 1. And I'm going to be able to drop it. Okay, so I'm going to get sum for I. J equals 1 equals k plus 1 up to d. The Vj squared, that's going to, this term is going to be 1 times Vj dot ai squared. Okay. And now I can look at this term, and this, what's neat is that this term will be exactly equal to the all of A. Oh, I want to sum over J equals K plus 1 up to D. This term will actually be so I want to so I'm going to swap the order of the sums. Okay, I'm going to put this sum on here, and now the sum over all of the I coordinates times the vector Vj is going to actually be the squared norm of the whole matrix A times Vj. Okay, and so now this is going to be equal to J equals K plus 1 times D sigma J squared. Okay, which is what I'd promised you here. Okay, so we can actually, so this is, this linear algebra is something you would learn in like a linear algebra class to really go through and internalize it. But the point is the sum of the squared errors through the, because it's squared error, you get the Pythagorean theorem, you can factor all this out, you get they're captured exactly in the squared singular values. So kind of the SVD is also calculating how much error I have in this process too, right? Okay, I want to say I have, we're gonna talk about one more property. I promise you, let's go back here. I talked about how when we did this projection, we took our data, we projected it down to this basis, and there were two representations. We either had this k-dimensional representation, which we get from kind of taking the dot products with the right singular vectors, come out this magical equation that's built into Python for you, or we could get the d-dimensional representation, which is moving on. I think you probably saw how to do that, but I want to give another interpretation of that. And so this is called the best rank K approximation. Okay, so I want to have an A, which is going to be an N by D, and I want to map it to an A sub K, which is also going to be an N by D, and I want that the rank of AK to be equal to K, and I want to find the best one somehow. Okay, we have to define what best means. Okay, so I want the kind of the best Okay, so what does best mean? There are two kind of nice ways to define the best one. So A sub k, it can be the arg min over all these. Okay, rank of B equals k of B minus A, the Frobenius norm, or arg min of rank of B equals k of B minus A, the so the two norm, the spectrum. Okay, these are now matrix norms. Okay, remember the Frobenius norm took all the entries and squared them and then added them up. And this one had to do with the direction that maximized the difference. Right, that the two norm for matrices was a little bit more confusing. Okay, and so it turns out for both of these, for both they have the same answer. They have AK is exactly going to be J equals 1 up to K of sigma J Uj Vj transpose, where these are the top K kind of the singular vectors and values, right? This is Uj, Vj, and sigma J. Okay, so I remember we showed how to decompose A into these if I added from J up to K. Well, now I'm only taking the top K of them. Each one of these components inside the sum was going to be a rank 1 component, and I'm going to add up K of them, so the rank is at most K. It turns out because all the Uj's and Vj's are orthogonal from each other, that means that these are not going to be linearly dependent, and it's going to be rank K. Okay, so it's going to give me exactly something that rank K, and this is optimizing either the closest rank K solution under Frobenius norm or under the spectral, the two norm between the matrices. Okay, it turns out that this guy, that this term is exactly our sum equals I to n of AI, or it's, right, think of it this other way, projection of to B of AI minus AI squared, right? So this term, this first one, the Frobenius norm that's adding everything up, is exactly our sum squared objective that we want. Okay, why is that true? Well, it's what the projection is doing is it's projecting onto the best rank K approximation, or the best kind of thing from the first K singular vectors, right? This is giving me the projection onto these K. This term is exactly if I did yeah, so this is exactly giving me this projection onto these K singular vectors. And so the first one is is minimizing this. What's the second one doing? What is this one doing? This one is a little bit harder to understand. It's saying that I need to think about in like a little bit higher dimensions here. So let me draw a picture well, I think we can draw this in 3 dimensions, but now we're just going to project onto V1 here. I'm not going to give you an example with V2. I'm just going to project onto V1. And now I'm in 3 dimensions, and I'm projecting down onto here, onto okay, so I'm projecting down onto this line, but they're coming from a 3-dimensional space. Think of there's like a some cylinder of points, and they're projecting onto this thing here. What is this spectral norm measuring? It's saying, well, what is, after I've done the projection, I can look at just the residuals. Let me remove this one dimension and now look at a projection down onto a space, which is kind of like V2 and, well, and V3 that can define the space. Okay, so now my entire V1 is coming directly out of the plane. So now I'm looking down on here. I've just rotated this. So V1 is coming out here. And so now all of my data points probably look something like this. And they're all mapping down onto here. What is left, there used to be components of these coming out of the screen, but I've smushed that down. What's left is the projection onto this two-dimensional space. And now I'm finding the one direction, x, which is equal to 1, the direction that if I project onto that direction, it has the most. Okay, so I could look at the one direction that has the most error. How much error is on here? Okay, so the spectral norm of B minus A squared is equal to the max over X of the sum over I of the projection onto X of BI minus AI squared. Okay, so it's the projection onto the direction which maximizes each row of this matrix, the d-dimensional row, the sum of those square terms. What is that direction which maximizes the error? It's exactly the k plus 1 singular, right singular vector that's left. The last one I didn't yet incorporate, which in this case is V2. There's more variation in V2 than V3. I know that because they're ordered by the singular values and they're all orthogonal. And that's what the SVD gives me. So it's minimizing both of these. And this one, the error on the first, this one, let me write one more thing, we'll finish. This is the sum of j equals k plus 1 of sigma j squared. And this one is equal to just sigma k plus 1 squared. Okay, so it's just the k plus 1 singular value squared is what's left. This is all b minus k that are left summed up, and this is just the k formula. By Pythagorean, I can decompose them nicely, and so I get all these nice properties. Okay, so this is kind of a whirlwind through singular value decomposition. Hopefully, for your homework, you will play with it with some more data, and you'll kind of see with it, and you'll be forced to give these answers. We'll revisit some of this on Monday's lecture, and we'll see a little bit more structure related to eigenvectors, and we'll show how to actually compute it. We'll do all that in Monday's lecture. Hopefully, that version, you'll see some of this again, and it will start to sink in a bit more. I know it can be kind of a lot if you haven't seen this much before. All right.